Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, with our ongoing series on polynuclear hydrocarbons and heterocycles, we have today bring for you the another session. In our previous session, we have discussed on saturated heterocycles. Taking the lecture forward, today also we would be talking on saturated heterocycles, and for this discussion we have once again with us in our studios Dr. Vandana. Dr. Vandana is Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. So let's welcome our guest Dr. Vandana and let's try to understand more and more about saturated heterocycles. Hello ma'am, welcome to the lecture.
Thank you so much ma'am. Hello viewers, we have started a series polynuclear hydrocarbons and heterocyclic compound, and in this series we have discussed many compounds like thiophene, furan, indol, anthracene, naphthalene. And in the last lecture we have taken saturated heterocyclics and we have discussed what are saturated heterocyclics. Saturated heterocyclics are the compound in which only a single bond in a cycle along with a heteroatom will present. Means there will be no double bond or there will be no triple bond. It means there will be no unsaturation in compounds. These are saturated heterocyclics. And we have discussed interestingly about the conformations, about the stereochemistry of the compounds. In today's lecture, we have planned like rate of formation of saturated rings. What will be the rate of the saturated heterocyclics? The synthesis of 3, 4, 5 and 6 membered rings, cycloaddition reactions, thermodynamic control over ring size, Thorpe-Ingold effect, Baldwin's rules, exceptions to Baldwin's rule, ring size according to NMR studies. How can we decide the ring size of saturated heterocycles with NMR, cerulanin, indoxyls, icetin or dioxindol, indigo. And we will also discuss about the indol derivative, that is 1-hydroxybenzotriazole, or we can say HOBT. What will be the rate of saturated rings about the reactivity? You can see the order. 5 membered will be the fastest, then 6 membered, then 3 membered, then 7, then 4, then 8 to 10 will be the lowest. The reason for the two superimposed trends is two opposing factors. Firstly, small rings form slowly because forming them introduce ring strain. We have studied about the bare strain ring in ring. This ring strain is there even at transition state, raising its energy and slowing down the reaction. You know how reaction took place? First of all, the reactant reached to the transition state and this transition state then converted to the products. The activation energy for forming a 3-membered ring is very high. Why it is so? Due to the angle strain, but decreases as the ring becomes larger. This explains why 3 and 4 membered do not fit straightforwardly into the sequence, and you can see the sequence. The sequence is not in a proper order. But if the reaction rate simply depended on the strain of the product, the slowest reaction would be the formation of 3-membered ring and highest will be the 6-membered ring, which are essentially strain free. The 6-membered ring is strain free, would be the fastest one. Yet the data shows that 4-membered ring we have just seen form more slowly than 3-membered ones and 5-membered ones faster than 6-membered ones. So why this order is like that? Why? The answer is this. This is the equation we can apply. This is delta G. What is delta G? Activation energy. Delta is equal to delta H minus T delta S. The activation energy barriers, that is delta G of our reaction, are made up of two parts. First is this delta H, this is the enthalpy of activation, which tells about the energy required to bring atom together against the strain to make a ring, and repulsive forces they usually have. And what is delta S? An entropy of activation which tells us about how easy it is to form an ordered transition state. We have already said that a reactant converted to product via a transition state from a wriggling and randomly rotating molecule. Delta G and delta H for 3 and 4 membered ring are large. That is, energy is needed to bend the molecule into the strained small ring formation. But delta H for 5, 6, 7, that is for large ring, is smaller. Because of this, the second factor is one that depends on delta S. How much order must be imposed on the molecule to get it to react? Think of it. A long chain has a lot of disorder, and to get its end to meet up to make a cyclic, heterocyclic compound, the react means it has to give up a lot of freedom. So, for the formation of medium and large ring, delta S will be large and negative, contributing to a large delta H and hence slow the reaction. For 3 membered rings, the reacting atoms are already very close together, and almost no order needs to imposing the molecule to get it to cyclize. The 3 membered ring is fast and the product is strained, so the delta H will be large. 4 membered rings form slowly as compared to 3 membered ring, and the product is still significantly strained, but the reacting atoms are now not right next to each other as it was in 3 membered ring. 5 membered ring formation is often fastest of all, significantly less strain, and ends are still not too far apart. 6 membered ring formation experiences no strain, but neither does it have the advantage of ends being close. 7 membered rings and beyond that more slowly as delta S increases. About 4 membered ring, oxytane for example and acetidine are considerably less reactive towards ring opening reaction. It is strain relieving, nucleophilic processes than their 3 membered counterparts. Oxytane reacts with hydroxide anion 10⁻³ times more slowly than it does with oxirane. But oxytane will react the organolithium reagent in the presence of boron trifluoride, and acetidine is opened on heating with concentrated HCl. This is the reaction you can see. This is the oxytane ring and how it opens with the help of this organometallic compound N-butyl lithium, and acetidine with concentrated HCl and heat, it will open like this. So, these are the ring opening reaction of 4 membered ring. The most important 4 membered system is undoubtedly the beta lactam ring, which is present and essential for biological activity of penicillin and cephalosporin antibiotics. These are the structure you can see, 2 beta lactam containing antibiotics. This is penicillin G and this is cephalosporin C, and you can see the structure heterocyclic, saturated heterocyclic, this one and this one. Beta lactams are very susceptible to ring opening via attack at the carbonyl carbon, in contrast to the 5 membered analogous pyrrolidones or acyclic amides, which are resistant to nucleophilic attack at carbonyl carbon. In addition, beta lactams are hydrolyzed by a specific enzyme, beta lactamase, the production of which is a mechanism by which bacteria become resistant to such antibiotics because of this structure, beta lactam structure. Substitution of the acetoxy group, you can see this is the 4-acetoxy-acetidone by nucleophiles in an important synthetic method. The reaction proceeds via addition to an intermediate. What is this? You can see this is the intermediate and this is what? this is imine because of this double bond at nitrogen atom. This is called imine, either than by direct displacement. So, you can see this substitution by this acetyl group and with this azide group N3. Beta lactones or propiolactones too are readily attacked at the carbonyl carbon. For example, they are particularly easy hydrolyzed compared with the simple esters, you know what are ester, RCOR, or 5 or 6 membered lactones. Now, 5 and 6 membered ring, pyrrolidine and piperidine, we have discussed in earlier lecture about these preparation and reactions, are somewhat better nucleophiles than diethylamine, principally because the nitrogen is less hindered. The pKa values of pyrrolidine is 11.27, for piperidine it is 11.29, and the typical of amine basis diethylamine, for example, 10.98. Piperidines like cyclohexane adopt a preferred chair conformation to reduce the strain. Both an N hydrogen and L alkyl substituent adopt an equatorial orientation. You can see these are the chair form, and you can see the N alkyl or N hydrogen both occupied the equatorial orientation. 3,4-dihydro-2H-pyran is an enol ether. It is widely used to protect alcohol with which it reacts readily under acidic condition. You can see this is the 3,4-dihydro-2H-pyran structure because of this double bond 3,4-dihydro, and on acidic it will give you the protected alcohol, but easily hydrolyzed back to alcohol under mildly acidic aqueous condition. So, you can see these are other structures. This is tetrahydropyran, this is 2H-pyran, 4H-pyran, these are the reduced pyran. A great deal is known about the hydroxylated tetrahydrofurans and tetrahydropyrans because such ring system occur in sugars. Glucose, you can see this is the alpha D glucopyranose. Glucose has two cyclic form hemiacetal containing a tetrahydropyran. However, many of the reactions of sugars involve a small equilibrium concentration of ring open hydroxyaldehyde. All 5 hydroxyaldehydes, 5 hydroxyketones and 5 hydroxy acids easily close to form 6 membered oxygen containing rings, lactols and lactones respectively. And you can see these are the two isomeric form. This is alpha D glucopyranose. Why it is alpha? Because this hydroxyl group is downward, and this is beta because of this upward. So, these are the two isomeric form of glucopyranose, alpha D and beta D. And this is another form, you can see ring open hydroxyaldehyde responsible for many reactions. You can see this is the open chain of this glucopyranose. Tetrahydropyran, like piperidine, adopts a preferred chair conformation. We have discussed about the conformation in last lecture. 2-alkoxy tetrahydropyrans prefer a conformation in which the alkoxy group, you can see this is the methoxy group OCH3, is axial, and this is referred to as anomeric effect. And about anomeric effect we have discussed in detail in last lecture. And you can say if we see these two structure, it will be more stable because this group is axial, and if we say this, you can see this will be more stable. Synthesis of saturated heterocyclic compound. This is the general scheme for the synthesis of saturated heterocyclic compound. And what kind of mechanism there? Intramolecular nucleophilic substitution. 5 and 6 membered saturated rings can be prepared by reduction of corresponding aromatic compound. The most general method for making all ring sizes is by cyclization of an omega substituted amine, alcohol or thiol via an intramolecular nucleophilic displacement or substitution. The rate of cyclization goes through a minimum at the 4 membered ring size, and 5 and 6 membered rings are by far easiest to make. So, these rings can be easily made because of angle strain, or we can say ring strain. You can see this kind of long chain compound and HZ, where Z can be a nitrogen heteroatom, it can be a oxygen. If we say it is nitrogen, it will be amine, omega substituted amine, or if it is O, then it will be omega substituted alcohol or thiol when it is sulfur, when Z is sulfur. What it happens, you can see this heteroatom with lone pair of electron can attack to this carbon atom, and when it attacks to this carbon atom, it imposes to leave this position. So, substitution will take place, and you can say, and you can see this kind of ring will be formed. And what kind of ring, how many members in the ring, it is according to this end. Oxytanes and epoxides can be prepared by cyclization of 1,3 halo alcohols or 1,2 halo alcohols, we can say halohydrins respectively. You can see this is cyclohexene, NBS and bromosuccinimide. First of all, you can see what happens over here. A bromo group is attached to this, and then with sodium hydroxide it will give you this kind of epoxide. Aziridines can be prepared by alkali catalyzed cyclization of 2 haloamines or 2 hydroxyamine sulfonate ester. You can see these are the aziridine and can be prepared by 2 haloamines or 2 hydroxyamine sulfonate ester. Azitidine, what are azitidine? You can see this is the azitidine, can be obtained by cyclization of 3 haloamines. Thetanes, tetrahydrothiophene and tetrahydrothiopyranes can all be prepared by the reaction of appropriate omega dihalide. You can see this is the dihalide structure with sulfide ion, sodium sulfide, and the sodium salt of omega hydrosulfide is the intermediate. You can see this is the intermediate and this is the product. Thetane, cyclization involving heteroatom attachment to an alkene via complexes with cations such as bromo plus, iodo, mercury, palladium are useful methods because they give products with functionalized side chain. You can see this is the side chain for further transformations if you want to make further saturated heterocycles over here. How it took place, you can see this is the transition state and we have to show within the big brackets of transition state. How it took place, you can see first of all this cation will attack to this like this in this transition state, and after that this Z with a lone pair of electron attack to this electrophilic carbon, and you can see this kind of product along with the side chain will formed. 3-membered heterocyclics from alkenes. By far the most widely used method for the preparation of epoxides involves oxidation of an alkene by a per acid. What is per acid? Nothing but when a extra oxygen within the per acid, it is called per acid, via a direct one-step transfer of an oxygen atom. More highly substituted alkene react fastest, showing that electronic effects are more important than steric effects in this reaction. Steric effects do, however, control the facial selectivity of the epoxidation. What does it mean, facial selectivity? It means which kind of phase will attack to this reactant, either this side or this side, and you can see it is attacked from this side, or you can see the bulky group is the opposite side. Right. So, steric effects are working here. You can see first of all this alkene when react with PSC6H5 COOOH, this is per acid, and you can see this transition state how it took place by cyclization. You can see this is a concerted mechanism. What is concerted mechanism? When bond breakage or bond formation within the two reactant took place simultaneously. This is called concerted mechanism. Hence, we get this kind of epoxide ring. Several other direct oxygen transfer reagent. You see over here what happens, a oxygen is transferred from this per acid to this alkene to formation of a epoxide. Several other direct oxygen transfer reagents have been developed, of which by far the most important is the Sharpless reagent. What is Sharpless reagent? It is a mixture of hydroperoxide with the titanium isopropoxide and a dialkyl titrate. You can see this is the reaction which shows epoxidation due to Sharpless enantioselective, that is product will form with enantioselective. The structure of reagent is complex, but it reacts readily with alkenes containing polar groups. For example, allylic alcohol. You can see allylic alcohol which can coordinate with the metal. The most important feature of this process is that when enantiomer tartrate esters are used, a highly ordered asymmetric reactive site results, leading in turn to high optical induction in the product. So, you can see you can choose the enantiomer of the product, which product you want in the high yield. N-tosyl aziridines can be obtained. You can see N-tosyl group, this is TS, and aziridine because N present within the 3-membered ring can be obtained directly from alkenes by reaction with chloramine T. What is chloramine T? You can see this is tosylate group, this is nitrogen, chloride and Na. When you took excess of chloramine T, you will get what? This N-tosyl aziridines. Now, how can we form saturated heterocycles? By through interchange of heteroatoms also. You can see this is a saturated heterocyclics when oxygen is there. Now, you can see in the product the oxygen atom get displaced by sulfur atom. But one more thing you can notice over here, the stereochemistry. You can see the bond, these are dark bond and this is dotted. So, stereochemistry will get change in the product as compared to the reactant. The most common method for the preparation of thiorenes is via reaction of an epoxide with thiocyanate, thiourea or a phosphine sulfide. Stereochemistry of the thiorene is opposite to that of the starting epoxide. We have already discussed this. How it took place? You can see this is what? Triphenyl thiophosphine. And first of all, what happens? It attacks to this. So, this bond will break up and this kind of intermediate form, and you can see these are the more canonical structure of this intermediate, and at the last you will get this kind of product. How it took place? You can see how it took place, and phosphine will get as a side product. Now, cycloaddition reaction. Many methods have been developed for beta-lactam synthesis. The most widely used method being 2-component couplings. Here coupling reaction which occur either via concerted cycloaddition. I have explained just few minutes back what is concerted cycloaddition. The bond formation and bond breakage within the two reactant took place simultaneously or via 2-step mechanism. Here you can see the cycloaddition. First of all, these two reactants form this kind of intermediate, and with sodium bicarbonate you will get this kind of acetidonone by the addition of an isocyanate. This is what? Isocyanate, thionyl chloride, isocyanate. Now, what is the thermodynamic control over the ring size? Over the 3-membered ring, 4-membered ring, 5-membered ring and 6-membered ring. We have discussed in today's lecture and in the last lecture the kinetic control. Now, we are going to discuss about the thermodynamic control. There are many ring forming reacting that are under thermodynamic and not kinetic control. We will discuss these reactions. Glucose exists predominantly as a 6-membered ring in this solution. If you have studied about the glucose, you found it that it exists preferably as a 6-membered ring while in solution. It could also exist as a 5-membered ring, but it does not, because Although 5-membered rings form faster than 6-membered, but they are usually less stable. So, we have to see the stable factor over here. Remember, a 6-membered ring is essentially strain free when we have discussed about the bare strain theory. For similar thermodynamic reasons, it does not exist as a 7-membered ring, even though you can draw a reasonable structure for it. You can see this is the 6-membered ring of glucose, and this is the cyclization of hydroxyl 5-membered ring, and this is the cyclization possible hypothetical cyclization of hydroxyl gives 7-membered ring. But you can see what statement is there, neither of these is formed. In solution, this kind of a structure found because of stability or because of free strain. Thermodynamic control is important in other ways in carbohydrate chemistry, because control over ring size allows selective protection of hydroxyl groups of sugars. By comparing these two reactions, here are two reactions you can see, this is mannitol when reacts with benzaldehyde along with H2SO4, and here is the reaction mannitol when reacts with acetone. Both of them give acetals. You can see that both of them give acetals, but the ring size is different. Here you can see it is the 6-membered ring, and here you can see it is the 5-membered ring. The important thing is that acetone reacts with mannitol to form 3 5-membered acetals, or we can say dioxolanes, while benzaldehyde to only 6-membered acetals. This is a quite common result when there is a choice. Acetone prefers to react across a 1,2-diol to give a 5-membered acetal, while aldehyde prefers to react across 1,3-diol to form 6-membered acetal. Why it is so? We will discuss in coming slides. Drawing an informational diagram of the product on the right help to explain why all the substituents are equatorial and making this a particularly stable structure. Now imagine what would happen if acetone for this type of 6-membered ring acetal. There would always be an axial methyl group, and 6-membered ring would be less stable. So, we will explain by Thorpe-Ingold effect. What is that? The rate of ring formation, you can see how when a ring is formed through this open chain structure, it is not affected just by ring size, but by the substituents on the ring being formed. You can see here only chloride ion is present, while here you can see these two methyl groups. So, the rate of formation is also affected by the substituent present in the open chain reaction, and K relative is the relative rates. The second looks as though it suffers more steric hindrance. Here you can see because of these two groups there is a steric hindrance, but nonetheless it is 10,000 times faster. Why it is so? You can see the relative rate, this is 4 into 10 to the power 4 for this. Adding substituent to other ring forming reactions make them go faster too. Two examples the product are oxytanes and pyrrolidines. Here you can see oxytanes and pyrrolidines. You can see these are the how it took place. This oxonium ion when attacked to this carbon, it leaves this and cyclization takes place. Here also all these examples you can see. Here oxonium ion, then chloride ion will leave. Here amino group is there with lone pair of electron, it attacks to this carbon. So, bromide ion will leave and this kind of cyclization is there. Here again NH2 and you can see these kind of. So, this effect is quite general and is known as Thorpe-Ingold effect. The presence of substituent will faster the reaction. So, and after the first chemist to note its existence in 1915. So, we have discussed about the Thorpe-Ingold effect, that when steric hindrance or we can say some examples are observed when substituents are present, the rate of reaction becomes faster. So, hope you understood these things, the rate of ring formation and the cycloaddition reaction. In the coming lecture, we will discuss about the Baldwin rule and the exceptions to Baldwin rules and some derivatives of indole also. Thank you so much. In the saturated heterocyclics part 2, we have discussed about the rate of ring formation. We have discussed for 3-membered ring, for 4, 5, 6 and many more. And we have discussed about the cycloaddition reaction and Thorpe-Ingold effect. We will continue with this effect. Why it is so? That when bulky groups are present in the long chain and it is cyclizes to give a cyclic saturated heterocyclics, so why it is faster reaction when alkyl substituents are there? The Thorpe-Ingold effect is the way in which substituents on the ring increase the rate or equilibrium constant for ring formation reaction. It is not only rate that can be affected by additional substituent. More substituent means more cyclized product at the equilibrium. The Thorpe-Ingold effect is both a kinetic and thermodynamic phenomenon. You can see over here how cyclization and what is the rate of reaction for this kind of cyclization. This is a 5-membered ring and it is also, you can see, when 2 alkyl groups are there, the rate relative rate is 14 as compared to 1, and when 4 alkyl substituent, when alkyl substituent increases, the rate will also increases. Why it is so? The explanation comes in 2 parts. Number 1, more applicable to the formation of small rings. If you measure the bond angles of chains of carbon latums, you expect them to close to tetrahedral angle, that is 109.5 degree. Another, the crystal structure of 1,3-dicarboxylic acid in the margin shows carbon-carbon-carbon bond angle of 110 degree. Now imagine adding substituent to the chain. This will repel the carbon atom already there, force them a little closer, then they are making the bond angle slightly less. X-ray crystallography tells us that adding 2 methyl groups to our 1,3-dicarboxylic acid decreases the bond angle by about 4 degree. We can assume that same is true in alcohol starting material for epoxide forming reactions. Now consider what happens when both of these alcohols form an epoxide. The bond angle has to become about 60 degree, which involves about 50 degree of strain for the first diacid but only 46 for the second. By distorting the starting material and the methyl group have made it slightly easier to form a ring. This part of argument works only for the small rings, not for the large rings. Then what is for large ring? For larger rings we need another explanation, and it involves entropy. So entropy concept is there. What is entropy? Disorderness in a molecule. Pyrrolidine forming reaction as an example. We have explained the effect of entropy of activation on the rate of ring forming. When larger ring form, they have to lose more entropy at the transition state. We have discussed it, and this contributes to a less favorable delta G. Here you can see lowest energy conformation, many other possible, high entropy, lots of free rotation, you can see first, second and third. Here very negative deltas to get a transition state. Here you can see substituents repel group and limit flexibility. It can also take place from here and from here. Few conformations possible, lower entropy. Here you can see delta is less, but when the starting material has more substituent, it starts off with less entropy. More substituent means that more conformations are no longer accessible to the starting material. That, for example, methyl group hindered rotation of the nitrogen heteroatom and the methyl bromide substituent into the region of the space. Of those fewer conformations, many approximate to the conformation in the transition state, and moving from starting material to transition state involves a smaller loss of entropy. The same argument applied to the entropy of the reaction as a whole, the difference in entropy between starting material and the product. So, increased substitution favors ring closure even under thermodynamic control. Now, another rule, Baldwin rule. Nearly all the cyclization reactions that we have discussed have been intramolecular, that is substitution by nuclear reaction, where one end of the molecule acted as the nucleophile and displacing the leaving group at the another side. But you can imagine making saturated heterocyclics in plenty of other ways. Intramolecular substitution at the carbonyl group, you can see this is the carbonyl group. For example, such when happens in the lactonization reaction, or intramolecular addition of oxyanion onto an alkyl. Here you can see, here in substitution not takes place at the terminal but at the in between. Cyclization reaction can be classified by a simple system involving, according to Baldwin rule, first of all, the ring size being formed where the bond that breaks as the ring form or inside, that is endo, if it is outside, this is exo when ring form, and the new ring whether the electrophile is in sp, sp means diagonal, the stereochemistry will be diagonal, sp2 hybridization, the stereochemistry will be trigonal, or sp3 hybridization tetrahedral atom. This system places 3 of cyclization. We can categorize into 3, like what? The ring being formed has 3 members and the breaking of carbon and bromide bond is outside the new ring, it will be exo. You can see this is tetrahedral, or we can say in short tet. The ring being formed has 5 membered ring and the breaking of C double bond is outside the new ring. You can see over here outside the ring, and the carbon being attached, it is trigonal or sp2, or you can say trig. The ring being formed has 6 members and the breaking carbon-carbon bond is inside the new ring, it can endo, and carbon being attacked, it is a diagonal, that is sp, or we can say in short dig. Not all cyclization of open chains are successful, even though they may look fine on paper, but these are very difficult in actual. The guidelines that describe which reaction will work are known as Baldwin's rules, empirical observations backed up by some stereoelectronic reasoning. Reactions can be classified according to these rules, favored and disfavored. A reaction can happen favorable condition, or we can say this reaction will not happen, or we can say disfavored. Here are 2 quotations according to Baldwin rules. All exotet cyclizations are favored, that is cyclization from the group exo will be tetragonal are favored, while all exotrigonal also are favored. We will see in coming slide how these are. Despite the variation in rate, we have described this type of reactions exotet cyclization and have no stereoelectronic problems. That is, you can see how this is the open chain, this is a heteroatom with lone pair of electron, this is another heteroatom, or we can say this is a nucleophile or vice versa, and the lone pair of this nucleophile and the CX, CX means this is carbon and this is heteroatom with anti-bonding orbital, X is the leaving group, can overlap successfully irrespective of the ring size. Whatever the ring size, they can overlap, like this orbital of lone pair with nucleophile can overlap with this anti-bonding orbital of this. So, the same is true for exoteric trigonal reaction, and it is easy for the nucleophilic lone pair to overlap with CGX anti-bonding pi orbital. We have discussed about the sigma orbital, that is for this, and for pi orbital you can see over here these are the pi bond and these are the orbitals, and this is the orbital of this group, that is Y having a lone pair of electron. So, overlapping is possible over here, here also and here also, while we are talking about this sigma bonding, that is with one single bond, or while we are talking about this double X pi anti-bonding. For example, lactone formation. 5 and 6 endo-tetrahedral are disfavored. Endo-tetrahedral reaction would not actually make a ring. Here you can see this is an example, but they fall conveniently into the system. Here you can see no ring is formed over here. However, a hypothetical arrow are there that this kind of ring can be formed, but these are not formed. The arrows in the reasonable looking mechanism on the right described as 6 endo-tetrahedral process. Why it is 6 tetra? When you start from here, 1, 2, 3, 4, 5, 6. So, a 6-membered ring can be formed. Why it is endo? Because the making methyl bond is within the 6-membered ring truncheon state, even if no ring is formed. How it is took place? First of all, you can see what happens when it reacts with base. You can see there is a abstraction of proton from this side. So, negative charge come over here, and then again you can see the rearrangement. This will group attack to this, and here this kind of. So, is 6 endo-tetrahedral cyclization is possible? No, it is disfavored. But Eschel-Moser shows that for all its appeal, this mechanism is wrong. He mixed together the starting material for the reaction above the hexadeuterated compound for clarity. If the reaction had been intramolecular, the product would have contained either no deuterium or 6 deuteriums. In event, what found? The product mixture contained 25% of these compounds, each of these compounds, that is no deuterium along with 6 deuterium, and with a further 50% containing 3 deuterium. So, all kinds of products are there. The products cannot have formed intramolecularly in fact, and this distribution is exactly what would be expected from an intermolecular reaction. So, no intramolecular, as we have seen in last slide. This is just a hypothetical, but actually what happens? You can see from here when CD3, this hydrogen get replaced, CD3 and CD3 over here 6 hydrogen get replaced by 6 deuterium. So, this kind of intermolecular mechanism will take place within the 2 reactant. With endo-trigonal reaction, whether they work or not depends on the ring size. Now, 3, 4 and 5 endo-trigonal are disfavored. 3, 4, 5 this is the ring size, while 6-membered and 7-membered endo-trigonal ring are favored. Here we are talking about the formation of ring of these formation. How? With endo-trigonal. The reason we say this is the 5 endo-trigonal cyclization are reaction that look perfectly fine on paper, and at first sight it seems quite surprising that they would not work. You can see this can be easily when you see this kind of reaction. So, we probably assume that this kind of cyclization will take place, but actually it is not. Here you can see why it is not takes place. Simply it can take place easily. This amino group is a nucleophile, and this oxygen atom being an electronegative atom can attract these pi bonded electron towards itself, and this kind of cyclization, or we can say 5 endo-trigonal can take place, but it is actually not. This intramolecular conjugate addition, why it is? Because conjugation is there, conjugated carbonyl compound. Addition appears to be a reasonable way of making a substituted pyrrolidine. but this reaction does not happen. Instead, the amine attacks the carbonyl group. In spite of attacking this amino group to this carbon, it will attack to this carbonyl. How? We will see in the coming slide. So, it is favorable reaction, and we can say 5-exotrigonal cyclization is favored. Here you can see the comparison between these two. This is the hypothetical, and actually what happens, this kind of mechanism actually happens. This amino group, or we can say this nitrogen with lone pair electron, attack to this carbonyl carbon. Why it is so? Because of this. So why is 5-endotrigonal so bad? The problem is that the nitrogen's lone pair has problems reaching round to this carbon, or we can say pi anti-bonding orbital of the Michael acceptor. There is no problem reaching as far as the electrophilic carbon is concerned in the plane of this substituent, but if it bends out of this plane, which is must, if it is so overlapped with pi anti-bonding orbital, it moves too far away from the methylene carbon to react. You can see it is very far away. So it is like a dog chained just out of reach of a bone. You have chained a dog and it cannot reach to the bone where it is very far. You can see what actually the stereochemistry is here. You can see it is bad alignment. You can see this carbon, how it overlap with this anti-bonding pi orbital, and here you can see it is too far away because distance. Lengthen the chain, thou the dog gets its dinner. Here is perfectly straightforward 6-endotrigonal for which orbital overlap presents no problem. So you can see what kind of cyclization is there. First of all, when this reacts with base, it will detach the proton, and this kind of oxonium ion is formed because of this abstraction of this proton from here, and then cyclization. How it takes place, you can see this electron will convert it to here, and this kind of bond will follow the 6-endotrigonal cyclization and yield is the 89%. Now exceptions to Baldwin's rule are these are rules followed by every reaction? No, only few of reactions followed the Baldwin's rule, while few reactions are not followed this Baldwin's rule. Baldwin's rules are only guidelines, and when a reaction is thermodynamically very favorable and there is no other possible pathway, 5-endotrigonal reaction can take place the formation of cyclic acetal from a carbonyl compound and ethylene glycol. We do not need to give again the full mechanism here, but you should check you can still write it. The key step with regard to Baldwin rule is shown within an arrow in a coming reaction. It is a 5-endotrigonal reaction, but it works. You can see how it took place. This kind of cyclization is there. 5-endo, why it is 5-endo? 1, if you start 1, 2, 3, 4, 5. So this hydroxyl group along with this oxygen acts as a nucleophile, and these lone pair of electron can attach to this carbon. So it is 5th number carbon, that is why it is called 5-endotrigonal. Why it is trigonal? Because double bond is there, and this carbon because of this oxonium ion become electrophilic in nature. So cyclization is there. You can see the formation of cyclic acetal or dioxolane from a carbonyl compound and ethylene glycol. In fact, cations frequently disobey Baldwin's rules. Other well-defined exceptions to Baldwin's rule include pericyclic reactions. You know what are pericyclic reactions? When a reactant can convert it to product without any chemical reagent, or these reactions are initiated by heat or by photons. The reactions in which second raw atoms such as sulfur are included in the ring. You can see this is the example. This 5-endotrigonal reaction, this sulfur analog of the amine cyclization that did not work is fine. Carbon sulfur bond are long, and empty 3d orbitals of sulfur may play a role for providing an initial interaction with the carbon-carbon, this is, we are talking about this carbon-carbon pi bond. So, first of all what happens? The base abstract a proton from here, and now this sulfur with this electron can attack to this electrophilic carbon, and 5-endo trigonal cyclization took place, and this kind of saturated heterocyclic compound are there. With tetrahedral and trigonal cyclization, exocyclic is better than endocyclic with diagonal cyclization, and the reverse is true. If we are talking about the tetragonal and trigonal endo, the reverse is true. All endo diagonal cyclizations are favored, that these are move from S endo trigonal to 5 endo diagonal, and the reaction become much easier. Even 4 endo diagonal reactions work. Here you can see the example. First of all what happens? No doubt there is a base which will detach this proton from here, and what happens? 1, 2, 3, 4, 5, this kind of cyclization, 5 endo diagonal. Why it is diagonal? Because of presence of this double or triple bond, and followed by hydrolysis you will get this kind of product. Look out for 5 endo diagonal trigonal reactions. They are disfavored, even though on paper they look fine. We expect you did agree that these endo diagonal reactions look awful on paper. The linear alkyne seems to put the electrophilic carbon well out of each of the electrophile. Even further away than in 5 endo trigonal reaction, the important thing with endo diagonal cyclization that alkyne has 2 pi anti-bonding orbitals, one of which must always lie in the plane of the new ring, and making it much easier to nucleophile to get it. Now 3 and 4 exodiagonal cyclizations are disfavored, and 5 to 7 exodiagonal cyclizations are favored. Baldwin rules and ring opening. Baldwin rules work because they are based on whether or not orbital overlaps can readily achieved in the conformation required at the transition state. But the transition state is the same whether the reaction is going forward or backward. The principle of microscopic reversibility what say? That if a reaction goes via certain mechanism, the reverse reaction must follow exactly the same path in the opposite direction. So, Baldwin's rule also applied to ring opening reaction also, not only to ring formation but also ring opening reactions. This is where the unfavorability of 5 endo trigonal really is important. For example, in tetrahydrofuranil ester, to do an E1CB, that elimination unimolecular elimination with base. You can see here. Indeed, when it is treated with methoxide in deuterated methanol, it exchanges the proton alpha to the ester for deuterium, providing that inert forms, but it does not eliminate. Elimination would be a reverse 5 endo trigonal process and is disfavored. Here you can see why it is so, because this pi bond and sigma anti-bonding orbitals are orthogonal, so they cannot interact. We have already stated that Baldwin rules depends upon the overlap, if overlapping between the two orbitals, or we can say the orbital of lone pair of electron and the orbitals, anti-bonding orbitals of sigma bond or anti-bonding orbitals of pi bond can overlap. What happens over here? You can see first of all this methoxide ion first of all abstract this proton, and you can see what kind of cyclization is there. So, this reverse is not possible. Why it is so? Because these two orbitals cannot interact with each other. So, this kind of product possible over here. Whenever you think about a ring opening reaction, consider it is reverse and assess whether it is favored according to Baldwin rules. Baldwin rules can be summarized in a chart. You can see this is the chart. These are the endocyclization, this part show, and this part show again exocyclic reaction. Here you can see tetrahedral, trigonal, diagonal, this you can see disfavored, and these are, here you can see this is the 3-membered ring, 4-membered ring, 5-membered ring, 6-membered ring, 7-membered ring. These are, you can see respective chart, you can see these are favored cyclization, these are disfavored, and these are also disfavored. You should note the general outer line of this chart. Endotetragonal and endotrigonal are disfavored. We have seen from the chart, exotetragonal and exotrigonal are favored, and the reverse for diagonal cyclization. Then you just need to learn the cutoff points, and that indicate the exception to this broad brush view. 6 endotrigonal falls into the favorable category, and while 4 exodiagonal falls into the disfavored one. If you really can remember only one thing, it should be that 5 endotrigonal cyclization is disfavored. Here is the chart. Now, how can we define the ring size according to the NMR spectroscopy? You know what is NMR spectroscopy? It is nothing but is nuclear magnetic resonance. We see the proton, the kind of proton, we can determine the size of ring, the saturated heterocyclics ring size. We considered the effect of changes in the dihedral angle on coupling constant. But the dihedral angle is not only the angle worth measuring, we should also consider how the 2 carbon hydrogen bonds are spread out in space. You can see this is the 3-membered ring, and we can show that what we mean of fixing the dihedral angle at 0, or see carbon hydrogen bonds are in the same plane, and looking at the variation of with the ring size of some simple cyclic alkenes. Here you can see as the ring size increases from 3-membered to 7-membered ring, the coupling constant is also increases. For 3-membered ring, it is 0.5 to 1.5. For 4-membered ring, it is 2.5 to 4.0. For 5-membered ring, it is 5.0 to 7.0. So, from values of J, from values of coupling constant, we can determine the ring size. The wider apart the hydrogens are spread, the smaller the ring constant. Remember, the dihedral angle stays the same 0 degree. We are just varying the angle in plane between these two hydrogens. A dramatic illustration of this comes with the product of dehydrogenation of the natural product gual and elemental sulfur. From the reaction mixture guazoline, a deep blue oil can be distilled. Here you can see this is gual. When reacts with sulfur 8 along with heat, it will give you guazoline. Here you can see these are some spectral data, delta H 8.21 H, and this is singlet. Again delta H value 7.6 for one hydrogen doublet and coupling constant 4.0, 7.37 for one hydrogen, that is doublet, and J value 11.0. So, from this data you can see the several peaks of equivalent proton. Here you can say for one hydrogen, and here you can see 3.02 for 1H, but it is a septate peak, and the J value is 6.9. So, from this value you can calculate which kind of ring is formed. How? Some assignment are clear, that is 6 hydrogen doublet and 1 hydrogen septate are the isopropyl ring. If you know about the nuclear magnetic resonance, you can easily conclude this 6 hydrogen doublet and 1 hydrogen septate, and this is doublet 6 hydrogen. We can't really say which belongs to which. How? 1H singlet must be the hydrogen as it has no neighbors. 1H singlet must be no neighbors, and that leaves us 2 coupled pairs of proton. One pair J is equal to 4 Hertz and other J is equal to 11 Hertz. From the values above, we expect to find larger coupling where hydrogen carbon hydroxyl angle is smaller. So, we can say that 4H coupling is between the pair on 5-membered ring, these are the protons, and 11 Hertz coupling in between the pair on the 7-membered ring. So, here we can say that on the basis of NMR studies, or we can say coupling constant more precisely, if you see the data, if you see the peaks, you can determine the ring size of saturated heterocyclic compounds. So, today we have discussed about the rate of formation of ring. Today we have discussed about the Ingold rules and Baldwin's rules, and we have also discussed about the exceptions to Baldwin's rules and how can we determine the ring size of saturated heterocycles bar NMR studies. So, hope you understood this lecture. Thank you so much.
With this note, thank you ma'am, thank you so very much, and dear friends, thanks for watching us too. We would be meeting again soon. Till then, take care, goodbye.